Hi, my name is Kristen Phillips, and this is my final presentation on alternating circuits. I also talk a little bit about alternating currents as well. The audience that I am choosing to gear this presentation toward is high school students. So they have a basic knowledge of imaginary numbers, so they can work with operations with imaginary numbers and complex numbers. They know how to do some computations with it, but they have some very simple basic knowledge of it. They also have some knowledge of direct circuits and currents, and they may have also been introduced to alternating circuits and currents. It might kind of depend on specifically what grade level I'm working with. Obviously, if I'm working with my freshman classes, their knowledge of alternating circuits or currents might be very minimal, whereas if I'm working with my CIS pre-calculus classes, they might have a little bit more knowledge about that. So when I was thinking about what presentation I should do for this, I wanted to come up with a topic that students can also relate imaginary numbers to or complex numbers to outside of math class. So first, just some basic knowledge of imaginary numbers that I expect the students to know. They should know that I is denoted as the square root of -1, and I squared then is -1. This is a challenging concept for students because we constantly hear, oh, it's an imaginary number, this isn't important in the real world, when am I going to use it? So coming up with alternating circuits and currents to use, I thought, hey, it's another class that they can see how it's used outside of math class. So in their physical science classes, working with complex or imaginary numbers. So when coming up with a definition, I really wanted to find a definition where students might get a visualization as to why this is important. So I stumbled upon this definition of complex numbers. It's a mathematical quantity representing two dimensions of magnitude and direction. I really enjoyed this definition because right now, students really only think of complex numbers as a plus bi. So rather than getting them to think about complex numbers as always being a plus bi or x plus iy, switching their thinking towards dimensions and magnitude versus direction, because they do a lot of vectors in physical science. So getting them to make that connection as to, oh, maybe complex numbers are a little bit more than just numbers with I. Okay, so then we introducing what alternating currents are with students. Alternating currents is an electric current which periodically reverses direction and changes its magnitude continuously with time. So right there from that definition, that tells us that having to deal with direction and magnitude, we need different dimensions when dealing with numbers. So we can get by with just using our real numbers, but when we involve some complex numbers, some of our calculations become a little bit more easier to work with. So for example, electricity changes between positive and negative in a sine wave. When we combine currents, it would be ideal for us to be able to identify a new current. So if we're trying to identify a new current, but the current is currently working through positive and negative sine waves, it's going to be a little bit harder unless we have complex numbers to work with. So these complex numbers allow us to be able to easily calculate the quote-unquote new current that the electricity might be floating between. So again, alternating currents, just to give a visualization as to what we're talking about here, the currents can move in either direction to, for say, example, light this light bulb, and then a sine wave is formed from it. So alternating current circuits, we are working with quantities of voltage, current, and resistance. Clearly, they are not one-dimensional quantities. Again, we could get by with just working with the real number system, but computations then get to be ugly really fast. And by allowing us to use complex numbers, our calculations become quite easier. So our currents are alternating in direction and amplitude. So again, multidimensional type quantities that we are working with. Frequency and phase shift are also two of these dimensions that need to also be considered. So again, a lot of things going on in alternating currents here. So we need to work with mathematical objects and techniques to represent these multi-dimensional qualities. So by using complex numbers, we are able to represent amplitude and phase shift as an alternating current waveform. Okay, and in doing so, we can also use complex numbers to express amplitude and phase shift at once. Okay, so now we are able to combine some equations involving amplitude and phase shift, whereas if we were not using complex numbers, we would have too many things going on and it would get nasty. So one way for students to get a visualization of this, so they might be like, okay, well, I understand that A plus BI, but how does that really work multidimensionally? I like to have them think about a number line pointing in different directions. That might give them a better idea of, okay, well, if my number line is pointing straight north, and then I have a number line pointing straight west or southeast, how do I represent all of those different components? And our complex numbers allow us to do so. So unlike direct currents, we need to have another way to compute these multidimensional values. That's why imaginary numbers are so useful for alternating currents. And again, I know students have just a basic understanding of alternating currents and circuits, but giving them an understanding as to why complex numbers can be used outside of math class. We have a lot of students that go out into the trade and work on becoming electricians, and I think this helps them relate to this topic and seeing and fully understanding why complex numbers gives us a multi-dimensional representation, and that honestly makes these lives a lot easier.